Okay, we're finishing up this unit, taking a look at beta-adrenergic receptor signaling, and then we'll be moving over to finish up this actual unit, talking about acetylcholine signaling, just so that we can work the other second messages into the game that we haven't talked about yet. Okay, so what we're looking at to kind of wrap up this discussion of beta-adrenergic receptor signaling is why is it so complicated? Okay? And so one of the things that we looked at to start that off was physiological flexibility. Okay? And that is, you don't necessarily want to get an all or nothing physiological change in every single situation that you're going to activate this pathway. You want a grayscale. You want a graded response. And you may not necessarily want to get the same magnitude of things changing all of the time. Okay? So the three cell types, or two cell types, and three scenarios we were looking at were the following. Okay? And I've just put them up here just so you can sort of see the differences. All right? Now, the first thing to understand, and again, go back and understand, that the only component in this pathway that can be upregulated 50%, starting from a zero baseline and going up 50%, is GPK. The GPK has calcium inputs and it's got phosphorylation inputs. Everybody else is pretty much all or nothing. Okay? So, if we take a look at GPK, we've got three scenarios where we can see a change in its activity. All right? The first one is, again, looking at a liver cell treated with epinephrine. Now, this is a normal cell, nothing weird. You're not adding an ionophore. There's no mutation, no cholera, no caffeine. Everything's normal. Okay? So if you take a look at the pathway in a liver cell, again, normal, treated with epinephrine, then as you guys know, we're going to get graph 1 over there. Okay? The standard bell curve. And that's just the standard 100% response that you're going to get to look at the activation of GPK when everything gets activated in the pathway. We get the calcium side and we get the phosphorylation side. Okay, well now you move over to muscle cells. Now we've got two ways we can go here. Now if you were to combine a neuronal impulse with epinephrine, then you would also get graph 1. Okay? But at the same time, understand that with muscle cells in culture, we can separate the nerve impulse activation of the pathway from the epinephrine activation, because we can add those two separately to the cell. We don't have to do them together. So if you do that, you notice, okay, now the other two graphs here, 2 and 4, we both get a half activation of GPK. It only comes up 50%. But what's interesting isn't the amplitude, it's the shape. Okay? So one of those two graphs corresponds to what would happen if you took a muscle cell and activated it with a nerve impulse, which is only going to trigger the calcium-dependent pathway. No phosphorylation. The other is what epinephrine does, without calcium. So the question is, can you guys tell which of those two belongs to the neuronal impulse and which one belongs to the epinephrine? What do you guys think? It's kind of interesting when you put the two together, you get graph 1. If you split it into the two components, you get either of those two appearances. Okay? So which of those two do you think would match up with calcium, the nerve impulse? Yeah. What do you guys think? Shout it out.
Graph 2.
Okay, for calcium. Okay, anybody else? Come on, get them. Okay, jeez, come on. Okay, how many of you guys think calcium would do graph 4? Okay, it's graph 4. What's the difference between 2 and 4? 4 shuts down quicker. Okay? You notice that 4 goes back down more rapidly than 2. 2, it takes longer. Okay? What do we have to do to remove the effect of calcium? So if we get a partial activation by calcium with GPK, what do we have to do to reverse that? Drop the calcium. So as soon as the calcium concentration drops after the nerve impulse is gone, remember the calcium is basically coming in from outside the cell. We've got calcium-activated calcium channels. There's nothing else going on here. All we've got to do is pump the calcium out of the cell or back into the endoplasmic or sarcoplasmic reticulum, and it drops. We don't have to undo anything to GPK, so it's fast. So calcium plays a key role in getting the cell back to normal after the hormonal impulse is removed. And the way that you can see that is if you take a look at graph 2, that's the profile for what happens if you took a muscle cell and treated it with epinephrine, but you didn't have the calcium part of the pathway. You still get a half activation, right? And that's going to be due to pKa. That's going to be due to phosphorylation. But here's what you need to remember, is that in the absence of calcium, it takes you longer to come back down. And that's because you need the calcium-dependent activation to its maximum activity of the CAMP phosphodiesterase. If you don't maximally stimulate CAMP phosphodiesterase, pKa is going to remain active longer. Okay? pKa stays active longer, GPK remains phosphorylated longer. It means that the phosphatase remains inactive longer. So the difference here is, remember, if we're trying to reverse the effects of phosphorylation, it's a 2-part system. Part 1 is you have to shut the kinase off. Part 2 is you have to remove the phosphate that the kinase already put on the protein. So the point of going through this is it illustrates that calcium plays a key role not only in ramping things up, but as importantly, that increase in calcium that you normally see, for example, in the liver cell, is that it's vital to get you to shut things back down as rapidly as you turned them on in the first place. Okay? All right. More complications. The other reason it's complicated is that we're amplifying the signal. Okay? Remember that the starting signal of epinephrine that's going to interact, for example, with the liver cell is going to be in a nanomolar concentration range, 10 to the minus 9. After we go through all this stuff in the liver cell, we're going to increase blood glucose levels by half, up into the millimolar range. Nanomolar signal, millimolar physiological response, that's 1 million to 10 million-fold amplification. That's why it's complicated. You could not get that amplification if it was a linear pathway where everything was working stoichiometrically. Okay? So signal amplification is a big part of it. Okay? So now we've got physiological flexibility. We basically have signal amplification. Now we're bringing back redundancy. Now we already talked about the one example of redundancy in the system. And that is poor glycogen synthase up here being clobbered by 2 different kinases that generally can be switched on simultaneously in a liver cell, but they don't have to be. Okay? So you can independently switch on PKC or pKa. They're both going to do the same thing when it comes to glycogen synthase. Glycogen synthase has a single threonine that can be phosphorylated by either kinase. So pKa phosphorylates it, we shut it off. PKC phosphorylates it and shut it off. Remember, PKC requires both DAG and calcium for its activity. It's inactive, completely inactive in the absence of either one of those. Calcium is responsible for sort of changing the localization of PKC. That allows it to come up near the cytosolic leaflet of the plasma membrane, and that's where it can interact with DAG. We need both. So here's redundancy. Here's the other example of redundancy, and this takes us into the last part of the signaling chapter. It's a process called desensitization. It's kind of what's happening to all of this with the election. You're going, enough already. I don't want to hear these people. I don't want to see these people. And we're going to be stuck with one of them for 4 more years. Desensitization does the same thing in your body. Remember, these hormones are meant to be short duration, fast acting, and reversible. You've already seen how you screw that up with caffeine. That's right, take a big sip now. Remember, caffeine is perturbing how it should normally work. You don't want these physiological changes to be permanent. The resting state is you're taking glucose and popping it into glycogen. You're not breaking down glycogen to make glucose. That's abnormal. We don't want to do that. If you force the cell to do it and keep it up, your cells are going to say, to hell with it, I'm turning it off. And the way they turn it off is they go like this. And the way they do it is they're going to shut off the receptors. And you might think, well, what's going to cause epinephrine to be out there for a long time? Your favorite stimulus to do that, stress. Okay? Around next week, a week from today, you guys will be desensitized to the max. You're going to be stressed out. Here's how it works. And it's redundant. Your cells not only want to desensitize, they make sure there's a couple ways of doing it. Okay? So here's what desensitization does. If pKa is active longer than it should be, it's got 2 low affinity substrates. Okay? So now remember, the activity has to be around for a long time, like that extra cup of coffee. That's going to do it. pKa can directly phosphorylate serines down here on this final cytosolic region of the beta-adrenergic receptor. It phosphorylates them, and it's going to desensitize it because it creates a binding site for a protein called beta-arrestin. And it's literally going to arrest the beta-adrenergic receptor. And you're going to see it does 2 things. It keeps it from interacting with GS-alpha, and it also, look who else it recruits. Where have you seen these guys before? AP2 and clathrin. Not foam cell formation, but where do you see AP2 and clathrin at the plasma membrane? Endocytosis. You're going to pull your receptors off the membrane. So that's going to be the effect of phosphorylation. But to make sure this actually happens, and really happens, is pKa also, we got another kinase cascade. Here's the second one in the system. And it's a kinase called BARK, the beta-adrenergic receptor kinase. It only has 1 substrate. And when it gets activated by pKa, now we get redundancy at phosphorylating the beta-adrenergic receptor. Now, pKa gets turned on by so many different G-protein coupled receptors. If you think about it, pKa doesn't know who made it. Okay, so when you have elevated pKa activity in a cell, there's a lot of different hormones and a lot of different receptors out there that can make that happen. So pKa can actually phosphorylate any G-protein coupled receptor that elevates its activity. That is referred to as heterologous desensitization. That's a mouthful. Heterologous desensitization. It means it can desensitize by phosphorylating any GPCR that turned it on. BARK can only phosphorylate the beta-adrenergic receptor. Okay? So BARK can't phosphorylate anybody but its own receptor. That's called homologous desensitization. So heterologous just means you got a broad spectrum kinase like pKa that can phosphorylate any GPCR that makes it. BARK is only activated in such a way that it can only phosphorylate the beta-adrenergic receptor. Okay? So that's homologous desensitization. So desensitization is important because that's what allows the cell that if for whatever reason the hormone is out there for a very, very long time, your cells are not going to go into overdrive and keep the signal pathway going. Because what you can see then is that when the beta-adrenergic receptor is phosphorylated by either BARC or PKA, it binds a complex of proteins down here. These guys you don't have to worry about. But what they do is important. And that is they get in the way of the G protein being able to bind to the activated receptor. So in essence, what it's doing is preventing the hormone bound to the receptor from functioning as a gap. So we can no longer keep GS-alpha active because we can't exchange GDP for GTP. That shuts it down right there. So it's going to start reducing adenoid cyclase activity, and it's going to force your CAMP levels to come down. Okay? Even if the hormone's still out there. Now that's going to be, this is a quick acting response. As you guys know, the other process though is endocytosis. That takes longer. Okay? Remember, it's not a fast thing to basically pull in something from the plasma membrane, put it in a vesicle, uncoat it, and take it to the lysosome for degradation. That's slow. So this is the longer term effect. And that is endocytosis. So what we're doing with beta-arrestin is we're creating binding sites for AP2 and clathrin. And in essence, what's now happening is your cells are going to have fewer beta-adrenergic receptors on the plasma membrane. Okay? Now here's where it's insidious if we go back to our favorite drug of the day, caffeine. You guys have already seen caffeine is working inside your cells. Okay? So strike one, caffeine's a stimulant because it's inhibiting CAMP phosphodiesterase, so it's going to keep the CAMP levels higher. PKA is going to be active longer. Intracellular. Extracellular. It competes with that adenosine to bind its receptor. Remember, the adenosine receptor is kind of a counterbalance to what the beta-adrenergic receptor is doing. Beta-adrenergic receptor says ramp up, stoke up, get active. Adenosine receptor says chill. Here's the third thing that caffeine is doing. Intracellular again. Remember, caffeine is hyperactivating PKA. So caffeine is stoking desensitization. This is why you become numb and you sort of zombie out after you drank a lot of caffeine. You become just sort of zoned. Your reflexes are shot. Anybody who's driven for a long time, okay, after you stop, drink some coffee to try and stay awake, you notice how your reflexes are shot. It's because you desensitized your receptors. They're gone. So the point is, if a deer goes running out in front of your car, or if you have to have a quick reaction to a reflex, after you've been up for a long time and you've been down in caffeine, you're not going to be able to respond. Your receptors are long gone. Okay? So that's another reason you crash. Here's another one. Okay? I can't believe you guys are sitting there drinking coffee while we're talking about this. All right, heck with it. I don't have to do anything after this. Here's the other thing. Heterologous desensitization gets you in trouble too. Now think about it. You're stoked up on caffeine. What is it you're depleting out of your liver? Okay, PKA is running pretty strong. What's happening to all the glycogen? It's being broken down, converted to glucose, secreted into your bloodstream. Where's that glucose going? Into your muscle cells. You're supposedly doing something. You're burning it up. Okay? Now, your blood glucose then, under those situations, is dropping, right? Down, 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 down. Who normally kicks in and says, hey, your blood sugar's dropping. We need to raise it. Which hormone takes care of it? Who's up here? Your glucagon receptor. Because remember, your glucagon receptor, glucagon does the same thing epinephrine does. It's got a different agenda, though. Glucagon is activating the same pathway that epinephrine does, but it's doing it because your blood glucose is low. It wants to raise it back up. Well, if you've been stoking caffeine the whole time, your pKa is ramped up. Guess who's going to be desensitized just like the beta-adrenergic receptor? Your glucagon receptors are desensitized. So now, this is why you really crash, okay? You're not only burning up your glycogen stores in your liver, and your blood glucose levels are dropping simply because your muscles are burning it up, you're also crashing because the glucagon can't elicit the normal pathway to raise your blood glucose back up. Because pKa, because it's hyperactivated, is heterologously desensitizing your glucagon receptors. Okay? So the point is that we kind of laugh about it. We all take advantage of using caffeine as a stimulant all the time. But this is why it's got these physiological consequences. Okay? It's doing a lot in there to basically temporarily keep you stimulated, but there's going to be a heavy price to pay when it wears off. Okay? All right. So now we're going to switch gears. And we're going to look at a variation on a signaling theme. We're looking at it for two reasons. The first reason is it lets us get the other second messages into the game. Okay? It wouldn't be fair to leave out nitric oxide, cyclic GMP. That's not fair. So we got to get them into the race. The other thing that this illustrates is the movement of a second messenger from one cell type to another. So now we're looking at a signaling pathway that has to skip over from one cell to another. So the signaling pathway we're looking at is triggered by acetylcholine, or acetylcholine, however you want to say it. The target cells are your vascular endothelial cells that line your blood vessels. Remember back when we talked about LDL, and we talked about hypercholesterolemia. These are the cells that line your blood vessels, okay? We've got the intima space there on the outside of them. That's where all the bad stuff happens with excess LDL and foam cells, inflammation, remember all that good stuff? All right, we've got a space here. And what we need to do is that we need to have these cells regulate blood pressure by stimulating the contraction or relaxation of the smooth muscle cells that surround your blood vessels. Okay? So contraction is elicited by epinephrine because epinephrine can bind directly to receptors on the muscle cells. But relaxation requires the vascular endothelial cells. And that's going to be elicited by the hormone acetylcholine. Acetylcholine binds to GPCR. Now these guys, it's a real simple pathway. Look how quickly we can go through it. Acetylcholine receptor only activates GQs. GQs is the only trimeric G protein on those cells. So that means we're only going to activate phospholipase C. That means we get IP3, we get DAG, and here's where the one we need to focus on. IP3, of course, is going to give rise to increased calcium. Increased calcium inside the vascular endothelial cells binds calmodulin, and that activates, here's another target. So calcium calmodulin activates CAMP phosphodiesterase, it activates GPK, it activates the enzyme nitric oxide synthase, NOS. And it converts arginine and molecular oxygen to citrulline and nitric oxide. Nitric oxide is the equivalent of a biological neutrino. It's very small, it's a gas. It can diffuse right out of the cells. Nitric oxide is the active ingredient in nitroglycerin that was first used over 100 years ago to treat individuals with coronary angina. that is muscle tension and pain and hypertension, high blood pressure, because of constriction of these muscle cells. So when you take a nitroglycerin tab, what happens is as soon as you ingest it, it's immediately broken down into glycerin and nitric oxide. The nitric oxide that you take in goes right to these muscle cells, and it's going to cause them to relax. Acetylcholine does the same thing. Acetylcholine binds to the endothelial cells, generates nitric oxide, which diffuses across the intimal space, and it goes straight into the muscle cell. Is this hormone signaling? Is this a hormonal response? We got a diffusible molecule, but is it a hormone? What do you think? Yes or no? No. There's no receptor. There is no receptor. So it's not a hormone. It basically goes from this cell into these cells, and it directly activates guanylyl cyclase. We don't need a G protein to do it. Nitric oxide does it. So guanylyl cyclase synthesizes cyclic GMP. Takes GTP, converts it to cyclic GMP. Cyclic GMP activates PKG. Same way cyclic AMP activates PKA. All you're doing is swapping A for G. No difference. PKG, when it is active, causes your muscle cells to relax. Okay? That's going to cause these blood vessels to vasodilate. It's going to lower your blood pressure. Constriction raises blood pressure, dilation reduces it. It lowers it. It's a chill factor. Okay? Now, guanylyl cyclase converts cyclic G, generates cyclic G. We've also got a cyclic G phosphodiesterase. PDA1 is the CAMP phosphodiesterase. PDE5 is the cyclic G phosphodiesterase. Okay? So now can you guys take a look at this and see you've got two ways you could come up with ways of lowering blood pressure. One is nitric oxide. Small molecule, diffusible, comes right into these cells, activates PKG through cyclic G, causes vasodilation, reduces your blood pressure. The other thing that you could do, think about it pharmacologically, is let's target the phosphodiesterase. What the phosphodiesterase inhibitor would do is basically keep cyclic GMP levels higher. That's going to hyperactivate PKG. That would also have an effect. Okay, so given the prevalence of hypertension and high blood pressure out there, drug companies were going after PDE5 inhibitors. Okay? The reason it would be attractive is that nitric oxide is very, very short-lived. If you take a nitroglycerin tab to elicit nitric oxide, the nitric oxide has a half-life of seconds. So the problem with using nitric oxide as a therapy is that its half-life is so short, you're constantly having to take it. What you could do to mitigate that is try and knock out PDE5, because that would keep the cyclic G levels up higher after nitric oxide did its thing. So the drug company said, there's money to be made, let's go for it. Here's what they were finding. Now think about it. Caffeine inhibits PDA1 because it looks like adenine. Well, the drugs they came up with to target PDE5 look like guanine. So here's the drug that they came up with, the very first one. It's this compound all here called sildenafil. We know it generically as Viagra. That's what it is. There's the structure. Okay? Take a look at it. It's got a purine ring. Looks very, very much like cyclic GMP. So in fact, it's analogous to caffeine, because what it does, it binds to PDE5, inhibits the cyclic GMP phosphodiesterase, and would allow cyclic GMP levels to remain higher. Classic drug discovery, drug design. You got an inhibitor, you put it out there, and you put it in clinical trials. Most of the individuals that suffer from hypertension and high blood pressure who are going to be the candidates to take this drug are going to predominantly be middle-aged, late middle-aged men. Okay? That's your target cohort. So, the good news. Turns out, it's a really good inhibitor of PDE5. It works pretty well. The bad news is that the guys that were in the clinical trial found it really wasn't that effective on its own at reducing coronary angina or high blood pressure. Didn't really do that great a job of dropping their blood pressure. But the men that were in the study, that were part of the clinical trial, went to their docs and said, by the way, there's a side effect going on here that you might want to know about. And that is, it turned out that because it's a vasodilator, it increases blood flow in the penis. And so many of the men that were in the clinical trials for using this for coronary angina or hypertension also suffered from erectile dysfunction. The drug companies go, ka-ching! We've got a drug that we cannot use for what it was originally designed for. We're going to move it right over here. They're among the most prescribed drugs on the market. They are major, major money makers. That isn't why they were designed. That isn't what they were intended for. These drugs were repurposed. And the reason is that they're very, very, very effective at treating ED, not so good at treating coronary angina. Okay? So it turns out they do work as vasodilators, just not for the blood vessels that they were targeting in the first place. But now this leads to an interesting scenario. And if you happen to watch any of the ads for Viagra or Cialis or any of them, where they show the guy and the gal sitting, now you can take your own individual packs. They're sitting next to each other in two separate bathtubs, which makes no sense. It's like watching Ozzie and Harriet. What? Why are they sitting in separate bathtubs? This isn't going to do anything. Okay, but when you watch the ads, notice the litany of side effects. Okay, they go through in the commercials with these massive side effects. If you have an erection lasting longer than 8 hours. Okay. I guess if you first went to the Guinness Book of World Records and then you go to your doctor, you might want to report that. But the other thing that they report is there's a danger. And there's a danger if you're taking an ED drug like Viagra and you're taking nitroglycerin to treat your hypertension. Okay? And there was a movie that came out a few years ago. It has Keanu Reeves and Jack Nicholson, a few people. There's a brilliant scene that illustrates the danger of this. So I'm just going to show it.
How are we doing? Doctors at 30 minutes, chest pains, nausea, shortness of breath, pulse 104, respirations 18. To the CDC, CMV, cardiac ambulance, KG. Mr. Samuel, I'm Dr. Mercer. Are you in any pain right now? You suppress your right chest. It's real tight. Show me what the pain is. Right here. What were you doing when the pain started? I was just beautiful. Of course. Unfortunately, no. Says Gene, that's he would ask you to take off finding perhaps an hand. Mr. Central, the EKG shows you have a blocked artery which is not allowing enough oxygen to get to the heart. Heart attack, we're going to stop it, but I need to know what medications you take. I take Lipitor. Cheers. Anything else? For blood pressure. What about Viagra? Mr. Sanborn, did you take any Viagra today? Mr. Sanborn? No. No Viagra. Okay, no, just need to be sure because I put nitroglycerin into your drip. And if you had taken Viagra, the combination could be fatal.
Okay. So, if you watch the commercials, you guys actually see that's one of the side effects you have to be careful about. Because if you took nitroglycerin, which is a very effective coronary vasodilator, you take that in conjunction with Viagra, you run the risk of having your blood pressure drop to 0. Okay? You will over-dilate. And so they actually use that as a joke line in the movie to basically illustrate it. Okay? So the point of going through this, yeah, it's funny, but now you guys have a good appreciation of this other little signaling pathway. Okay? Here's what's interesting. These are the main ED drugs that are out there. Levitra, Cialis, Viagra. They were all designed, again, to treat hypertension. Okay? They were all used as vasodilators. If you take a look at the variations, though, this is how different pharmacy companies, drug companies, can design different inhibitors. You notice the structures are all unique. They all share that common structure of resembling guanine. The other modifications are basically to increase solubility, to basically allow it to be transported across the plasma membrane, stability, so it's not metabolized. But the neat thing about all three of these compounds, just to show you, is you can actually take all three of them and you can molecularly dock them into the catalytic site of the phosphodiesterase. So you can actually design these drugs and modify them, not just by brute force chemistry, but you can use what's called computational docking. And that is, if you know the active site of an enzyme in its structure, three-dimensional structure, you can actually take computer models of that enzyme and virtually move different small molecules into the binding site and find ones that will dock. And in essence, what you can do is it allows you to save a lot of time on actual drug synthesis to narrow down the types of candidates that you might want to use for a particular treatment. And that was done to expedite the synthesis of all three of these compounds that you see here. Okay? So very nice because it illustrates a couple different aspects of drug design. But again, it also shows, look at the commonality of what these drugs have with caffeine. Caffeine is an adenine analog. It binds CAMP phosphodiesterase. These drugs are all guanine analogs, and they inhibit PDE5. So if someone were to ask you, what's the common mechanism of caffeine and ED drugs? You never would have thought that there's a relationship between the two of them. Okay? But if you ask somebody what's the common mechanism, they're both phosphodiesterase inhibitors. And physiologically, what they also have in common is they'll both keep you up all night. There. Okay, enough. Okay, here's where we're starting up. I want to get started on this to show you what's coming up next. We're going to focus on the cell cycle, cell division cycle. This is really the transition that goes into the cancer section of the course. Okay? So the first thing that we're going to do is look at how the cell cycle, cell division cycle, that cells go through occurs normally. And then you're going to see that cancer is an aberration of the normal signaling pathway that causes cells to go into the cell cycle, and it's also going to perturb the ability of the cell to stop or arrest the cell cycle. Now, the neat thing about the cell cycle is the following. You guys saw at the beginning of the signaling section, it was a lot of laboratories over many, many years that all provided insights and pieces of understanding cell signaling. What you see with the cell cycle is that all of our understanding of this process can literally be traced to 3 laboratories that were all working in the 1980s. Okay? 3 laboratories, 3 different countries. Lee Hartwell's the American. And here's what it's going to show, illustrate. The use of 3 different model organisms to understand the cell division cycle. Each one of them provides a piece of a puzzle. You wouldn't have solved it with any one of these organisms. You really required all 3 of them and the complementary approaches that all 3 of these labs did. And here's how they worked at it. Hartwell is a yeast geneticist, works on Saccharomyces cerevisiae. He took the same approach to study the cell cycle that Shackman did to basically look at the SEC pathway, secretory pathway. Instead of looking at SEC mutants, though, Hartwell's lab is looking at CDC mutants. That is, these are genes, you mutate them, you shift them to the non-permissive temperature, the cells stop progressing through the cell cycle. He found more than 100 of these genes. Pretty complicated. He called the genes CDC genes for cell division cycle. So instead of SEC, we're now dealing with CDC genes. We've already talked about one of them. It's going to come back, not to haunt you, but it's going to come back. CDC42, the little guy that's involved in branched microfilaments at the plasma membrane, plays a role in cell division. So this is what Lee Hartwell did. In the middle now, over in London, actually he was at Cambridge at the time, then he went to London when he became rich and famous, the British scientist Tim Hunt. Tim is working with marine organisms. He's working with basically anything that's got eggs. Surf clams, sea urchins, amphibians. He's focusing on one particular part of the cell cycle, the transition from G2 to M. And that's because that's the transition that eggs have to undergo to mature and be fertilized. So he's working at one little part of the cell cycle. Hartwell, as you're going to see, focused predominantly on cell cycle genes that were required to go into DNA replication, S phase. Hunt's working on cells that are on genes that are required to go into mitosis. His contribution is he's going to discover these proteins that are called cyclins. And the reason is cyclins are going to be the drivers of the cell cycle. So when a cell goes from G1 to S to G2 to M, every time it goes around that clock, it has to make one or more cyclins. And then to get out of that part of the cell cycle and go into the next phase, it has to degrade the cyclin. So cyclins exhibit this periodicity. They come and go. So that's how they got their name, cyclin. The last person involved worked in Scotland at the time. And this was Paul Nurse. Paul's lab worked on a different type of yeast. This is the fission yeast, Schizo Saccharomyces pombe, literally schizo for split. Unlike the budding yeast, Saccharomyces cerevisiae up here, that goes through cell division by budding off, Schizosaccharomyces pombe elongate and then divide. What Nurse's lab did is he understood the connection, or worked out the connection, between cell growth and cell division. And that is, normal cells need to double in size before they divide. Makes sense? That way you wind up with two daughter cells that are the same size as the original. Nurse found there are genes that control or link when the cell will divide with cell growth. And he also made CDC mutants in Schizosaccharomyces pombe, where the cells took longer than they should to divide. They strung out the cell cycle. It was longer. So he called the gene that was involved with that string. You're stringing out the cell cycle. But more importantly, what he found, and it's my favorite gene in the entire course, is a gene that if you mutated it, the cells divide too early. They divide before they doubled in size. So now you can imagine what's going to happen to this cell. Every time it divides, it gets a little bit smaller, a little bit smaller. Ultimately, it divides itself into extinction. It's an important gene. Because the mutant phenotype made the cells smaller, and because he was doing the work in Scotland, they called the gene WEE1. WEE1. Because what the phenotype was, the cells got a wee bit smaller every time they divide. Hey, won a Nobel Prize. You can laugh. Here's why it's important. We1 is essential for making sure our cells double in size before they divide. If it doesn't work, you're weak. You get smaller every time you divide, okay? So we're basically going to be going through and looking at the cell cycle in the context of the major contributions each of these three labs provided. And it very, very nicely illustrates how you take the complementary use of these different model organisms and you get different insights combining biochemistry and genetics to basically understand a process like the cell cycle. Okay? So we'll really get into that on Friday. Have some more graphs for you guys this afternoon. And everybody watch Game 7 tonight. See if the Cubs can do it.